Good afternoon. Thank you for coming to my talk today. My name is Anant Kamath. I am a PhD student at the Philip Giosine group at the University of Chicago. Today I'm going to talk about our results on bright mid-infrared fluorescence in giant mercury selenide cadmium sulfide quantum dots. Mid-infrared detection using interband transitions in narrow gap semiconductors is a well-established technology. In comparison, detection using intraband transitions have several advantages. The intraband transitions span the entire infrared range from the long wave to the short wave, like we see in this tuning curve for mercury selenide quantum dots. Due to the sparse density of states of the holes, we see suppression of Auger relaxation. Though a lot of studies have been done on intraband transitions in the mid-infrared over a decade, the mechanism of non-radiative relaxation is still not well understood. In 2008, Anshu Pandey and Philip Giosine showed that the phonon bottleneck in the conduction band could be overcome by growing a giant shell on top of the core nanocrystals. They attributed the non-radiative decay as a faster energy transfer from the quantum dot exciton to vibrations on the surface. So we would expect a fourth power of the radius dependence of the lifetime with the size of the nanocrystal, which is what they observe experimentally. More recently, Sean from our group studied the fluorescence quantum yield of mercury telluride quantum dots at different frequencies and showed a remarkable agreement of the model with the experimental quantum yields. Though there is a great agreement at shorter wavelengths, the measured quantum yields are 1 to 2 orders of magnitude lower than the calculated quantum yields at 5 microns. So this led us to consider other mechanisms of relaxation. In 1999, Arakawa from the University of Tokyo proposed a simple model of coupling between the intraband excitation to lattice phonons. And using a simple two-level Wigner-Weisskopf formalism, they calculated the scaling to be 1 over energy squared trend for the lifetime. If we extrapolate this plot to 5 microns, the lifetime would be of the order of nanoseconds. More recently, in 2015, Han and Bester did a similar calculation using DFT, and they too saw the relaxation between the nanosecond and picosecond timescale. If this is true, this is very bad news for us because the relaxation is limited by an intrinsic property of the material, and there's nothing we can do about it. And this is in line with reported efforts for trying to get bright mid-infrared luminescence in quantum dots. Though efforts have been put over the years, there is only a marginal increase in the quantum yield, and it is still less than 0.1%. Apart from multiphonon relaxation, another possibility is trapping, like which is which is the major mechanism in the wide gap semiconductors. If trapping is a major mechanism, we would expect an exponential dependence of the quantum yield on the nanocrystal diameter. Using two limiting values for this exponential length scale, we have plotted a rough scaling of the quantum yield versus the uh, nanocrystal diameter for a core shell nanocrystal. If FRET is the dominant mechanism, then the lifetime would follow this trend in the red curve, which is the fourth power of radius scaling. And if it is dominated by multiphonon relaxation, the lifetime would be independent of the thickness of the shell. So from this plot, we can see that by growing a giant by growing a giant type 1 shell on our core, we can find what is the dominant non-radiative mechanism at play in the nanocrystals. Though efforts have been, though a lot of effort have been put to try to grow a giant shell on mercury selenide over the last 5 years, limited success has been observed due to the synthetic difficulty of working with the cores. So here we are reporting progress in growth of giant shells of cat sulfide or mercury selenide quantum dots. In the TM, we can see that the shell grows nicely up to 15 layers, which is a 5 nanometer thickness of the shell. In the TM, we can see the core shell, the XRD pattern, sorry, in the XRD pattern, the peaks narrow as the shell grows, and the crystal structure is maintained along the zinc blende structure of the core. And in the FTIR UV spectrum that we have over here, we see an increase in the cat sulfide edge as the shell grows, and the intraband absorption of the core is not destroyed upon growth of the shell. So this work is not yet published, and we're going to report the synthetic details in a paper soon. This is how a typical infrared fluorescence spectrum looks for the mercury selenide cat sulfide quantum dots. The peak at 2000 centimeter inverse is the intraband luminescence from the fraction of the dots which are n-doped, and the peak at 5500 is the interband luminescence from the dots which are not doped. Just by looking at this spectrum, we cannot calculate the fluorescence quantum yield since we do not know the doping fraction, and the quantum yield for the intraband and interband emissions would be different. The way we measure doping is shown over here. The black curve is the FTIR absorption of the 14 cat sulfide dots using an in situ doping method and subtracting the absorption spectra for the between the two samples. We get the change in the intraband absorption and an interband bleach due to the doping change. By taking a ratio of the peaks of the intraband absorption and the interband bleach, we can calculate the doping for a given FTIR spectrum of the core shells. And using this method, we have calculated the doping of the 8 cat sulfide dots to be 5% and 14 cat sulfide dots to be 33%. By measurement of the doping and the absolute quantum yield, we find that the quantum yield of the giant mercury selenide cat sulfide dots is 1.9% at 5 microns in films and 1.3% in solution. So this is a factor of 20 larger than the previous reported quantum yields at 5 micron, and it is by far the brightest materials in solution in the mid-infrared. Though we say that these dots are bright, the quantum yield is still 2%, and there is still a long way to go. But now we are entering a regime where these materials are showing promise for applications as mid-infrared emitters in LEDs and biological fluorescent tags. Apart from getting bright luminescence, the trend of the quantum yield as a function of thickness gives a hint at the non-radiative mechanisms at play. On the estimated calculated plot that I had showed at the beginning of the presentation, I have plotted the data for the quantum yields for the mercury selenide cat sulfide along with the PL lifetime measurements recorded by Chris in our group. Though there are only 4 data points and there is some disagreement for the thickest shells, the trend strongly suggests that Foster energy transfer is the dominant non-radiative mechanism. Apart from a fundamental interest, this understanding of this mechanism has a lot of practical applications because the performance of quantum dot infrared detectors is limited by the fast non-radiative decay. And the understanding of this mechanism shows that the direction for improvement of the detectors is clear. We need a clean method to do a surface exchange of the high frequency vibrations and do a ligand exchange to give ligands which don't absorb in the mid-infrared. In summary, we have discussed today our success in growth of giant mercury selenide cat sulfide quantum dots. They are 20 times brighter than the previous reported dots at 5 microns, and these have a quantum yield of 2%. The trend of the quantum yield versus thickness shows that Foster energy transfer from the quantum dot to vibrations on the surface is likely to be the dominant mechanism. This work was done in collaboration with Chris Melnichuk, who measured the lifetime data. I want to thank Dr. Shin Tang for preparing substrates for my measurements, members of the Talapin and Tokmakov groups for helpful discussions. This work was possible due to generous funding from the NSF ARO and instrumentation from the MERSEC. I want to thank my group members for their support, and I'm happy to answer any questions.